Quantum computing, encryption, and ethics. Every message you send, every password you create, and every online purchase you make relies on one thing: trust. That trust is protected by encryption. Quantum computing has the potential to break that protection, not just technically, but socially and ethically. This is not just a technology story. It raises questions about who controls information and who is protected or exposed in the future. How encryption works today. Modern encryption protects data using complex mathematical problems. The basic idea is simple. It's easy to lock information, but extremely difficult to unlock it without the key. Many systems rely on factoring very large numbers, which classical computers struggle with. Even powerful classical machines would take thousands or millions of years to break strong encryption. That is why we trust systems like online banking, medical records, private messaging, and government security. Right now, security depends on one assumption. Classical computers are too slow to break these systems. Why quantum changes the game? Quantum computing challenges that assumption. Using algorithms like Shor's algorithm, quantum computers can solve problems like factoring much faster than classical computers. This means encryption that is secure today may not remain secure. There is also a major concern. Encrypted data can be collected now and decrypted later when quantum systems improve. This is called a harvest now, decrypt later threat. The risks are serious for medical data, government intelligence, and personal identity information. It also affects global power. Countries investing in quantum technology, including China and the European Union, could gain advantages in cybersecurity and intelligence. Meanwhile, less developed nations risk falling behind, creating a quantum divide with higher stakes than the digital divide. Preparing for this shift requires new encryption methods, policies, and global cooperation, starting now across industries and education systems worldwide. Post-quantum cryptography. To prepare for this future, researchers are developing post-quantum cryptography. These are new encryption methods designed to remain secure even against quantum attacks. Organizations like National Institute of Standards and Technology are already working to standardize these systems. But transitioning is not simple. There's a difficult balance. Move too slowly and sensitive data becomes vulnerable. Move too quickly and critical systems may fail or break. This is not just a technical challenge. It's a strategic and leadership decision that affects governments, healthcare systems, and global infrastructure. The ethical dimension. Quantum computing raises a deeper question. Are powerful technologies neutral, or do they carry moral weight? Some tools are clearly designed for harm. Others, like quantum computing, are more complex. They can help discover life-saving medicines, or break the encryption protecting billions of people. In this way, quantum computing is less like a typical tool and more like a high-impact technology, similar in scale to nuclear or global surveillance systems. We've already seen how technologies like social media and algorithm-driven platforms can reshape society in unexpected and sometimes harmful ways. Quantum computing could have even greater consequences, especially if controlled by a small number of powerful organizations or governments. This raises serious concerns. Who controls the technology? Who benefits from it? Who is left vulnerable? Quantum computing doesn't just challenge encryption. It challenges trust in the digital world. The question is not whether this technology will impact security. It's whether we will prepare for it responsibly. Because in the end, the future of quantum computing won't just be defined by what it can do, but by the choices we make about how it is used, who it protects, and who it puts at risk.